About how our awareness of the structure of the universe developed. And then if you have any questions about the show or that material, then we can take a break and answer those questions, or Jeff can certainly help answer some of those questions as well. Well, we start, and we take some great leaps in time here, but our fascination with the sky, with the heavens, goes back as far as humans have been looking at the sky. We've always wondered for ages and ages what the sky is, what those lights in the night sky are, where they came from, and ultimately what's our place among all those objects. And even though with the passage of time we've answered a lot of questions, we've also started asking a lot more. Each set of answers seems to introduce a new set of questions for us. Now, in the 1600s, earlier than that, long before that, when people started to really try to reason things out, to try to understand the sky, they began to use their imaginations, and they made up patterns and pictures among the stars. When you look at the night sky here, some of you I know can recognize a couple of groups of stars here. And that's one of the ways that people learned to familiarize themselves with the sky so that it wasn't quite so foreign and frightening. It became more comfortable for them. I can recognize that group of stars. So people made them up. In some cases, they were able to connect the stars with lines and make little stick figures that were recognizable. You don't see them too well here, but people use their imaginations and they flesh those figures out to make forms like Orion the Hunter and Taurus the Bull, a few other figures like that. Different cultures had their own different versions of the constellations, and so you'll see a lot of those wonderful cultural differences if you look at different parts of the world. But then along comes Galileo, who revolutionized astronomy by using a brand new tool. That was the telescope. Now, he didn't call it the telescope at the time, and it wasn't anything like the telescopes that we have today. It was quite weak. The resolution was quite poor. He couldn't really see things very sharply. It didn't gather much light, but he could still see more than people could with their naked eye. Galileo's observations were truly groundbreaking because it showed people what things really looked like. When he looked at objects, he sketched them out in his notebooks, and he made drawings of things that he saw, including the sunspots that we can see, and that some of our docents here in the Sun Squad are able to show our visitors up on the roof. He saw the craters on the surface of the moon, the moons of Jupiter, the 4 biggest ones at least, and he also could make out something funny about the planet Saturn. He didn't quite know what it was, and his view wasn't quite as clear as this. He could see what looked like ears on either side of Saturn, ears or handles, but he could never really figure out what they were. But he saw them. And he also saw something else too. When he looked at the Milky Way, he saw that faint band of light crossing the night sky was made up of a multitude of stars, packed together so tightly. Even with his crude little telescope, he could tell that there were so many stars forming the Milky Way, he couldn't count them. He called these star clouds. So he was able to revolutionize our knowledge of what the sky was made of, or what it was really composed of, what things really looked like. Later scientists made improvements. Isaac Newton, for example, invented a different kind of telescope, which is still very popular today. But among the other things that Newton did, he was really a Renaissance man of science. Some say one of the greatest geniuses of science who ever lived. And one of the other things that he did was he discovered something unusual about the nature of light. He found out that you could pass white light, sunlight, through a prism and break it up into these colors. Now, other people had done that before, so he wasn't the first one to do that. But by recombining those colors through another prism back into white light, he showed that those colors were in the light itself. People thought that maybe it was the prism that was coloring the light somehow. Newton showed that that's not the case. He showed that those colors live in white light. And that would be a very, very important foundation for science later on. We'll see that as we go on a bit. As science grew and evolved, telescopes got better, and some astronomers looked farther into the sky than Galileo was able to, and they showed that there are more than just stars up there. There are also things that they called nebulosities. They didn't know what they were, but they weren't stars. There were these fuzzy objects, and the view that they had wasn't quite as good as you see here, or nor as beautifully colored. But the astronomers saw these nebulosities, and they said, okay, that's something else unusual that's up there. In fact, one astronomer, Charles Messier, in 1774, made up a catalog of these nebulosities. And that's because at his time, scientists were very, very interested in looking for comets. Comets were another very mysterious object that people wanted to understand better. Some thought they were omens of ill will, of misfortune. And whoever could find new comets in the sky was rewarded with monetary rewards, with new homes, with high positions. So finding comets was a very lucrative thing to do in the 1700s. And Messier decided to help the astronomers out by making up a catalog of all these nebulosities so that astronomers could avoid them. That's because they were confusing the nebulosities for comets. He said, no, don't pay attention to the nebulosities. I'll show you exactly where they are, so you can look elsewhere for comets. Well, arguably, the objects in Messier's catalog are more interesting than comets. Now we know that they consist of star clusters and galaxies and nebulae, fascinating objects. But at the time, people didn't know what they were. They were still just called nebulosities. But people tried to put all this together. And in 1755, Immanuel Kant, who was a German philosopher, came up with an idea. He said, maybe what we live inside of, maybe the band of the Milky Way, can be explained by the fact that perhaps we live inside a disk of stars, a lens-shaped collection which he called an island universe. And that band of light crossing the sky is our inside view looking along the plane of this disk. That was a neat idea. Now, if the name Immanuel Kant sounds somehow familiar to you, especially if you've been in Hofeld Hall just before the planetarium shows, every now and then there is this quote that comes up on the screen, which is by Immanuel Kant. It says, "Two things fill me with ever-increasing wonder and awe, the starry skies above and the moral law within." That was Edward Hofeld's favorite quote by Immanuel Kant. So that's why we show that on the screens there. That was one of the things that Mr. Hofeld's estate insisted upon. But Kant also came up with that idea of the island universe, of an isolated group of stars that was the Milky Way. Now, not too many people believed it at that time, but it was an idea that would later on take hold. In 1785, William Herschel tried to figure out what the shape of the Milky Way was by actually counting the stars in different parts of the sky. This took a long time. But what he did was he came up with a conclusion that agreed with Kant. He determined that the Milky Way was shaped like a grindstone, a large flat disk. And he agreed with that whole idea that we're looking along the plane of this disk, and that's that band of light that we see crossing the sky. That's the Milky Way. So that opened people's eyes. But people still didn't really know how big the Milky Way was. Herschel tried to make a few calculations, but he wasn't very accurate about them. But he did a few other things too. Herschel was kind of like Newton. He did experiments in a lot of different areas. Another experiment that Herschel did, which will tie into all of this later on, is he also experimented with the nature of light. He passed light through a spectrum, just like Newton did. But what Herschel did was he measured the temperature of the different colors that were split out. And one very important thing he did was he discovered that there was a region just beyond the red color of the spectrum which had more heat than the other colors. It was warmer in that invisible color. He called that invisible color caloric rays, heat rays. Today we call it infrared. And with this simple experiment, just by putting a thermometer just beyond the red end of the spectrum and measuring the heat, he detected infrared radiation and really opened up our understanding of the electromagnetic spectrum, which is a broad band of radiation that includes optical or visible light, but only as a very, very tiny part of it. It's a much, much broader band. But people continued working with light. They knew that they could learn something from this, especially when they looked at things that are far away. In 1814, Joseph Fraunhofer invented the spectroscope, and Jeff is going to tell you about spectroscopes and what you can do with them. But he also found that in the spectrum of the sun, in particular, and the spectrum of fire, he could make out these lines in those colors. He could split out all the colors of the rainbow from the white light, but there were lines there too. Sometimes there were bright lines, sometimes there were dark lines, and it turns out that what those lines were are basically they're the fingerprints, the optical fingerprints of the elements found in the objects that are giving off the light. And if you can identify the fingerprints, you can identify the element, right? And here we have a few examples of some of the spectral lines. They're as unique as human fingerprints. Each element has a unique set of lines, which you can see here in different regions of the spectrum, distributed in different ways. Different numbers of lines, different positions. But how do you identify those lines and identify the elements in one spectrum when they're all laid on top of each other? That's the tough part. And here we can see the spectra of several different elements. And this is something Jeff will show you too again. But we see several elements there. The one at the top is hydrogen, the most abundant element in the entire universe. And we can see that it has three strong lines. I don't know if this projection quite shows all three of them, but they're right there. Two lines in the blue and one in the red. I've marked their positions there. You can kind of get an idea of where they are. And in these spectra of different stars, well, we think we can see them there too. Because what's the one element that's common in all stars, we think? Hydrogen. That's what stars are made of. So in these stars, in the same positions there in the colors, you can't see them too well here in this image. But we see the lines for hydrogen in these spectra. But there are lots of other lines there too, all mushed into the same spectrum. It's like trying to identify somebody from their fingerprint if the fingerprints of everybody in the front row here are all mushed on top of the same spot too. That's not easy. And that's the challenge that astronomers face when they try to examine the spectra of various stars and other objects. Well, an important discovery that was made that had to do with the spectra of objects was derived from the work of Christian Doppler, who in 1842 said that the wavelength of starlight should be affected by the motion of the stars themselves. He thought that if the stars are moving away from us or moving toward us, then their lights should be compressed. The light waves should be compressed, and the color should be bluer. And if the stars are moving away, the light rays or light waves are stretched out more, and the color should therefore be redder. It was a simple idea that made sense, but it was maybe just a little too simple, because light doesn't work that way. The principle is sound, but it only works with sound, not quite with light. I'll show you the obvious way that does this. But what Doppler didn't realize was that the color of stars was related more to their temperature than to their motion. So that whole idea of stars moving away from you being the red ones and stars moving toward you being the blue ones, that doesn't work. But here in the famous, or maybe infamous, Hertzsprung-Russell diagram, which all astronomy students have to learn, the hotter stars are the bluish ones, and then as you come down in temperature, the cooler stars are yellowish, and then orange, and then red. So it's mostly the temperature of a star that determines its color, not its motion toward you or away from you. But the color of stars would be affected this way if the stars were moving at a significant portion of the speed of light, which they're not. So we don't see that effect. It's far, far more subtle than that. With sound, you can see the effect, or you can hear the effect, rather. In 1845, it was shown that this Doppler effect can be detected with sound. If you have something giving off a sound, and it's stationary, wherever you are standing around that object, you'll hear that sound. If it's giving off a particular tone, you'll hear that tone, unchanging. But now if the object is moving, especially if it's moving toward you or away from you, then if it's moving toward you, the sound waves will be compressed, squeezed together, and you'll hear a different pitch. If it's moving away from you, the sound waves will be stretched farther apart, and you'll hear a different pitch. And there are ways that you can experience that. If there's a car going by honking its horn, you can hear that. It's obnoxious, but you can hear it. With any moving vehicle, whether it's a car or a jet or a race car or an ambulance or a fire truck, if they're making a constant sound as they pass by, then you'll hear it change in pitch as it approaches you and then moves away from you. You've all heard that, right? Okay. So we're going to do that here, or we'll try it anyway. I'm not sure if this is going to work because this is not as loud as I thought it was going to be. This is a website called onlinetonegenerator.com. And if you go to that website and click on play, can you hear that? It's not going to work what I'm going to do later with the microphone unless I trust it. Right. The people in the front row can hear it. All right, let's try this. No. Still hear it? You hear it changing pitch? Yep. I got to hold on to this so I don't suddenly fling my phone across the room. You hear the pitch changing? That's the Doppler effect with sound. So if you want to try this, you can do that just by going to www.onlinetonegenerator.com. And when you swing your phone around your head in front of a crowd of people, don't let go. So that's how it works with sound. In 1848, a French astronomer, a French scientist, showed how it works with light. It's much more subtle than the color being changed by the motion of the object. It all has to do with those spectral lines that were found in the spectrum of the sun or fire. Those chemical fingerprints in the lines, in the spectra of various objects. If you split out the light from some object into a spectrum and find the lines, locate the lines, if the object is not moving, if it's stationary, the lines will be at a reference position. If the object is moving, particularly moving away from you, you'll see the same lines, but they'll be shifted over toward the red end. There'll still be the same number of lines, the same relative positions with respect to each other. They'll just be moved over. So what you have to do is identify those lines. When you do, you'll find that they're red shifted if the object is moving away. If the object is moving toward you, you'll see those same lines, but they'll be shifted toward the blue end of the spectrum. So then they're said to be blue shifted. So objects that are moving away from you have spectral lines that are red shifted. Objects moving toward you have spectral lines that are blue shifted. Right? Well, I don't know, I guess. Yeah. Okay. So astronomers made use of that. That was a very important finding. Because what it does is it tells astronomers whether things are moving toward us or moving away. And when astronomers began to look at the light of these different nebulae, or these nebulosities in Messier's catalog, they found out that a lot of them are red shifted. A lot of them are moving away. So that was interesting. And at the time, all these nebulae were still thought to be in the Milky Way itself. This was 1912. Now in 1917, just 5 years later, Albert Einstein started thinking about these new discoveries being made by astronomers, particularly the distribution of objects in space. He came up with the E equals mc squared, his theory of relativity and so on. He thought that there might be something that was needed in the study of the motion of these objects in space. At the time, astronomers were very concerned that if the universe were a certain size, certain mass, it would have gravity at some point. Gravity, being a very, very powerful force, would pull things back in together. Astronomers were afraid that the universe would collapse under its own gravity. That's not what they were observing. And in fact, Einstein came up with this idea that maybe we can explain the stability of the universe by adding in this factor that will push against gravity. He called it the cosmological constant. And he represented it with the Greek letter lambda. So he came up with this force that pushed and counteracted gravity. So people went along with that for a little while. And they, in the meantime, kept studying the sky, trying to figure out where things were, how big they were, where things are going. In 1920, things kind of came to a head, and astronomers staged this what they call the Great Debate about the scale of the universe, featuring two astronomers, Harlow Shapley and Heber Curtis. And they both had different views on things. Shapley argued that the Milky Way is the only galaxy in the universe, that the sun is far away from the center of the Milky Way. And one piece of evidence that he presented in his argument was that the rotation of one particular nebula called M101 had actually been observed. That meant it had to be close by, because if it had been far away, like some astronomers were arguing, then it had to be rotating so fast it would be moving faster than the speed of light, which is impossible. So that was his argument. On the other hand, Heber Curtis supported Immanuel Kant's idea that there were other galaxies. And he said that the sun is at the center of the Milky Way. So as you can see, both of them were right about some things and wrong about others. But it turns out that Heber Curtis was more right about galaxies. So, and he also came out later on that the rotation of M101 had not been observed. That was an error. And that also showed then that, hey, maybe this thing really is far away. Or at least it probably wasn't as close as Shapley had thought. In 1924, someone you've probably heard of before, Edwin Hubble, helped resolve this debate with some work that involved observing stars in another nebulosity. And he built upon the work of another astronomer before him, a female astronomer, Henrietta Swan Leavitt, who studied a particular kind of star called a Cepheid variable. This is a kind of star that pulses, changes its brightness at a certain rate. And the rate at which it changes its brightness is directly related to its absolute brightness. So if we see it changing its brightness at a certain rate, we know how bright it is. And that's what astronomers used as a standard candle. If you know how bright a candle is, you measure its brightness, you can tell how far away it is. And that's what they were doing with these Cepheid variable stars. We know how bright they're supposed to be. So if we look in the sky and see a Cepheid variable that's a certain brightness, we can calculate how far away it is based on that brightness. So that's what Hubble did. And he applied this to some stars that he observed in M31, which was at the time called the Andromeda Nebula. At first he thought all these objects he was looking at were supernovae, but then he found that one of them was a Cepheid variable. It pulsed, it changed its brightness. He found out exactly how far away it is. And what he found out, what he calculated out, was that this object inside the Andromeda Nebula was way outside what the boundary of the Milky Way was believed to be at the time. So with this observation, Hubble showed that there's a lot of stuff outside our galaxy. The Andromeda Nebula was actually the Andromeda Galaxy. It was a whole other island universe by itself. Hubble provided, this was observational confirmation of an idea that was suggested a couple of years earlier by Georges Lemaitre, who you see here in this shot with Albert Einstein. But Georges Lemaitre was a Jesuit priest who was interested in astronomy, and he had calculated out from Einstein's work that the farther away a galaxy is, the greater its redshift will be. That is, the faster it's moving. So the greater the redshift of an object, the farther away it is. That's an interesting idea, that's evidence, another suggestion that the entire universe is expanding, getting bigger and bigger. Now that's the idea that is proposed by demonstrations using things like balloons with dots drawn on them, or a raisin cake as it bakes in the oven and expands and the raisins get farther and farther apart from each other, or the hubs on what is now the public programs presenter's favorite toy, the Hoberman sphere. Have you seen those? They're that big compressed, and then you can pull them apart and they get a lot bigger, and the hubs on the outside, the outer surface of the Hoberman sphere get farther and farther apart. Just like the dots drawn on the surface of a balloon. As you blow the balloon up, the dots grow farther and farther apart. So there's more and more evidence for the idea that the universe is getting bigger and bigger. And this idea is often misattributed to Edwin Hubble. It wasn't his idea, although he provided a lot of work that supported it. But now it's known as Hubble's law, or Hubble's flow. But it established the idea of an expanding universe. And in the face of that, Albert Einstein had to admit that maybe his idea of some repulsive force that was pushing against gravity was wrong. So he recanted the idea of the cosmological constant. He said it was the greatest blunder of his life. Being a little overly dramatic, but yeah, he said, all right, never mind. In 1931, Father Lemaitre proposed the idea of what he called the primordial atom, also the cosmic egg. He said that if everything is currently moving farther and farther apart, then at some point it had to start closer and closer together, packed more tightly, more densely. So he suggested at one point in time, the entire universe was very, very densely packed together. George Gamow took that idea and blew it up. He said, yeah, this primordial egg is the original state of the universe. Then it exploded. And the force of that explosion is why we see galaxies expanding from each other. The energy released by that explosion is what formed the atoms, the elements that we see. And that was the development of this idea that the origin of the universe had its beginning in this great explosion. And that was what explained the expansion that we observed. A couple of, a student of George Gamow's, Ralph Alpher, and a colleague, Robert Herman, they estimated that since the beginning of that expansion, the temperature of the entire universe should have cooled to about 5 degrees Kelvin. That's about 450 degrees below zero. That was their calculation, but nobody paid attention to it. They later revised their estimate upwards, and then they brought it down again. But this was the first calculation of what the temperature of the universe should be based on that idea of Father Lemaitre's. Now, his British astronomer named Fred Hoyle said, now, he was favoring another theory of the universe called the steady state, in which the idea is that the universe has always been expanding, and always will. And to replace the stuff that's moving farther and farther apart, there's new stuff being formed between them. He had to explain where stuff was coming from, but that was his idea. And in a radio commentary in 1949, he said, we don't need this Big Bang idea to explain the expansion of the universe. And that's where the name Big Bang came from. The name stuck. And we've been stuck with it ever since. It's a horrible name. We'll get to that in a minute. Really, the error of that term, Big Bang, suggests that it was an explosion of a small object into a larger space around it. But it really wasn't. The expansion of the universe began everywhere. At first, the universe was very cold, very hot, very dense, very opaque, and then it suddenly became very, very rarefied, very transparent, very cool. Everywhere at once. Not here blowing up into there, but it changed state everywhere. From very dense, very hot, very opaque, to very rarefied, very cool, very transparent. That's a change in state. But people kept characterizing it as an explosion. And many still do. 1965, Robert Dicke, who apparently wasn't aware of Gamow and Herman's work, predicted that after the Big Bang, the temperature of the universe should have cooled down to a certain temperature. And he was actually building a radiometer, an instrument that he would use to try to detect this radiation and measure its temperature. He was working on it. At the time, a couple of other people, these two astronomers working for Bell Labs, were trying to fine-tune their equipment and get rid of a hiss they were hearing in one of their antennas because they were trying to communicate with satellites, but they couldn't get rid of this hiss that came from everywhere. And they measured its temperature out to 3 degrees Kelvin. And they said, you know what? I think we found it. They called up, they respected Dicke, and because he was an expert in radio communications and radio interference. They called him up and they said, we've got this signal, this hiss that we can't get rid of. It's coming from all directions. We can't get rid of it. It's everywhere. Dicke turned to his colleagues on his team and he said, boys, we've been scooped. For their discovery, Penzias and Wilson received the Nobel Prize in 1968. And the location of this antenna is now a national landmark. And there it is in brass, confirming the Big Bang Theory. The author of Dark Universe is Timothy Ferris, very well-known science writer, professor of English, very, very literate, graceful writer. He said, the name Big Bang is misleading, ugly, and trivializing. It's inappropriately bellicose, perhaps suitable to describing a dormitory brawl, but less so for the event thought to have spawned the starry skies. He thought it needed more dignity. So he talked Sky and Telescope magazine into hosting a contest to rename the Big Bang. This was in 1993. Some of you might remember this. As judges, he recruited Carl Sagan and Hugh Downs, who was at the time the president of the National Space Institute. There were more than 13,000 submissions. You want to see some of the names that were submitted? Metamorphosis, the bottom turtle, supersede, hubble bubble, let there be stuff, blast from the past, the spark in the dark, Buddha's burp, trip from zip, immaculate inception, primal pop, Jurassic Quark, and time in. I don't think these people got into the spirit of things. Oh, I should try to, yeah, right? You can't miss this. That's almost every astronomer's reaction. But if you don't recognize him, by the way, that's Neil Tyson, the director of the Hayden Planetarium in New York and the narrator of Dark Universe. And also who is going to be basically the star of a revival of the Carl Sagan Cosmos series. Remember that in 1980? Wonderful series on NPR. When we ran the planetarium show based on it in the old planetarium, after just a couple of weeks, all the staff were talking like Carl Sagan. But billions and billions. Beginning on May 9th, Fox is going to run the new version of Cosmos. Actually, not necessarily a new version, but a continuation. Narrated and hosted by Neil Tyson, again starting May 9th. That'll be interesting, and it's really fortunate that this is coming out at the time that we're running Dark Universe. So that's a kind of a double shot of astronomy and cosmology there that should be really interesting. So, what questions do we have from all of this? How old is the universe? We don't know. We can only define the limits that our ability to collect data allow us to see. And we draw logical conclusions from that. Right now, the current evidence points to the expansion of the universe that we see having begun 13.8 billion years ago. 13.8 billion years. How many galaxies are there? A lot. This is 2 million of them. That's 2 million galaxies. And some astronomers have estimated that there may be 100 billion galaxies. And they keep looking. Looking farther and farther. You may have heard of this. In 1995, the Hubble Space Telescope was used to focus on one part of the sky near the Big Dipper, which you can see in this image here. I'll outline it for you. But just above the handle of the Big Dipper is the spot that was focused on by the Hubble Space Telescope for about 10 or 11 days. And it came up with an exposure of a tiny spot the size of a grain of sand held at arm's length. So a tiny, tiny, tiny spot about that big. And in that spot, it found 3,000 galaxies. Now this was an area that astronomers didn't expect to find very much. They thought it was just a random blank part of the sky. But here in this little area, 3,000 galaxies in that tiny spot. no bigger than a grain of sand held out at arm's length. 1/10 the apparent diameter of the full moon. 3,000 galaxies here. There are 4 stars in this picture. Everything else you see is a galaxy. And these are corresponding to distances of about 12 billion light years. A few years later, in 2003, and then crossing over into the beginning of 2004, the Hubble Ultra Deep Field was taken in a part of a southern constellation called Fornax, which is not too far away from Orion, but pretty far south. It's a simple constellation, but in that one area just off the tip of Fornax is this region, again a very, very tiny region of the sky in which the Hubble Ultra Deep Field captures 10,000 galaxies. So imagine a tiny spot the size of a grain of sand hiding 10,000 galaxies. How many grains of sand would it take to cover up the entire sky? And how many galaxies would that be? A lot. And a few years after that, recently, the Space Telescope focused in on the center portion of the Ultra Deep Field and took what they called the Extreme Deep Field and saw another 5,500 galaxies. This is amazing stuff. And how far out do those galaxies go? So the harder they look, the farther they look, the more astronomers seem to find. There are more and more distant galaxies, older and older objects which we see out there. The latest from just about a week ago, a galaxy that they believe is about 13.2 billion years old. So how much of the universe can we actually see? Over time we've learned to see better, farther, sharper. How much can we see? Actually, not very much. And it's not just because these are all far away. There's something else going on too. Part of the universe simply can't be seen. In 1933, an astronomer named Fritz Zwicky calculated that the mass of galaxies in one particular cluster of galaxies was not enough to be causing the kind of motion that he saw. He looked at the visible galaxies, calculated out how much mass there should be there, looked at the motion of these galaxies and said, that's not doing it. There's got to be more mass there that we're not seeing that is making these galaxies behave the way they are. So he said there's got to be something that he called missing mass in that galaxy cluster. And another revolutionary idea that he came up with was that the mass of a large cluster of galaxies might be enough to bend rays of light like a lens, causing a phenomenon that has since come to be known as gravitational lensing. He was right. And he was proven right in 1979. Never lived to see it, but, or did he? No, there was a long time after him. But he came up with the idea of gravitational lensing, which is something that astronomers are using today to try to find farther and farther objects in space. One example of a gravitational lens is that object on the right called the twin quasar in Ursa Major. That was the first object found with a gravitational lens. Now, what is a gravitational lens? It's caused by the gravity of a very massive object between the observer and something else farther away. The gravity of the object bends the light of that object behind it like a lens. And this is something that Einstein's theory of relativity predicted, that mass, sufficient mass, could bend rays of light. So that allows the observer to see something behind that massive object that he otherwise would not have seen, or she. And so what they do see is an apparent image on either side of the mass. Follow that? Here are a couple of other examples of gravitational lenses where the gravity of something here, that is not necessarily visible, but something right here, is bending the light coming from this cart over here, which I'm blocking, but the light is bent around me so that you can see the cart. That's what we have in these shots here. That image, the Einstein cross, is actually 4 images of the same object surrounding a quasar. And in these other shots, those arcs of light that you see are the gravitationally lensed images of more distant galaxies behind the large clusters that you see here. In this one, it's a set of galaxies, or rather, it's 5 images of a single quasar that is behind that cluster of galaxies. So the gravity of these massive galaxy clusters is refracting the light around them and allowing us to see farther. And very recently, yet another Hubble field, this one called the Frontier field, is specifically using gravitational lenses. So it's looking at 6 different clusters of galaxies and trying to see what images are lensed by the gravity of those galaxies. And this was an old shot of a star cluster called, or a galaxy cluster called Pandora's cluster, Abell 2744. And this is the latest Hubble image of that same object, where you can start to see those faint blue arcs and other features around it, which are the gravitationally lensed images of even more distant galaxies. Now, apart from that, other work is going on. In 1989, NASA launched a spacecraft called the Cosmic Background Explorer, or COBE, to investigate the cosmic microwave background that was discovered by Penzias and Wilson in 1965. And what it did was it mapped this radiation coming from all directions. It came up with this artificially colored map, which we see a portion of here, which shows temperature differences in that radiation. And that shows the beginnings of differentiation when things began to clump. The universe was no longer completely uniform. So this is the first step in becoming the clumpy universe that we see today. For this work, George Smoot of Berkeley and John Mather of NASA got the Nobel Prize in 2006. And since the COBE spacecraft, subsequent spacecraft have done other observations at a finer resolution, and they've really gotten sharper looks at this differentiation, at the temperature differences in the background radiation, which show the transition from a completely hot, uniform, opaque universe to something that's a little lumpier, taking us to where we are today. So, the big picture that we have now is that 13.8 billion years ago, the expansion of the universe began. Call it Buddha's burp, or whatever you want. For the first 380,000 years, the universe was still too opaque, too dense, to allow any light to go from point A to point B. But after 380,000 years, it began to turn more and more transparent. And that's the image that we see in the cosmic microwave background. That's the first light that was allowed to shine across the universe. And then that led eventually to the formation of stars and galaxies, to the state of the universe that we have today. But there's more. A few years ago, astronomers found, in 1998, they found that as we heard in the show, in Dark Universe, by observing supernovas in distant galaxies, they determined that the rate of expansion of the universe changed 5 billion years ago. Now, they expected the rate of expansion to slow down due to gravity. But 5 billion years ago, it started to accelerate again. So something was pushing against gravity, preventing the universe from collapsing in on itself. Does that sound familiar? Was Einstein right? This is something that astronomers have called the dark energy. There's dark matter and dark energy. It's something they can't see. It's something they don't understand. It's dark. It's some kind of repulsive force. Let's call it energy. But if you ask any astronomer what dark energy really is, they won't be able to tell you. The one who does is getting the next Nobel Prize. But the current theory, again, as we saw in Dark Universe, is that dark energy is believed to comprise about 3/4 of the universe. Roughly 23% is dark matter. This is stuff we can't see, but we can detect it by the gravitational influence that it has on other objects. And a teeny tiny part of that is us. Less than 5% is atomic matter, also sometimes called baryonic matter, but it's you and me and stars and galaxies, the stuff that we can see. A recent development, just this year, is that the way some astronomers are phrasing this is that part of the web of dark matter that connects the galaxies has been seen for the first time. The energy of a quasar is illuminating this huge cloud of gas going out about 200 million light years, bigger than anything else they've seen before, and they believe that this could be a portion of the dark matter connection between one cluster of galaxies and another. Now, we've seen this very interesting depiction of dark matter in the show Dark Universe, and you've probably seen other images similar. Starting with this one, remember this is the survey image of 2 million galaxies. I showed you this before. But look at the structure that you see here. It looks kind of foamy. That very closely matches what's called the Bolshoi cosmological simulation, which is the most accurate model of the evolution of the universe to date. It has these ripples and filaments and web-like structures and looks rather foamy. So when you look at the head of a glass of beer, you're looking at the universe. I mean, it has that same sort of texture. You can pursue this farther if you want. But these are very challenging topics that are addressed in Dark Universe. I hope that all of you will see the show, the current final version of the show, in the planetarium, where you can see and hear it the way you should be able to, and where you get the latest tweaks in the language, and you'll hear it from Neil Tyson himself. So we finally have a narrator who knows what he's talking about. But there's a lot of other programming that we have that is relating to this. One of which is a new show in Hoffeld Hall. Now, for those who aren't aware of it, on certain days when the schedule allows it, we sneak in a different presentation between planetarium shows in Hoffeld Hall, which is just below the planetarium. So these are short 10, 15-minute shows that are created and produced by the planetarium's presenters. So we're very proud of this effort. And they did one that ties in to Dark Universe and talks about the cosmic microwave background radiation, how it was found, what it tells us, and that is shown, it'll be shown every day, every weekday at 12:40, but more often on weekends when there's a heavier show schedule, every 45 minutes. So Ancient Light is another presentation that we certainly encourage you to see. And another interesting activity that we're doing is going to be taking place for only 3 days near the end of February, when the planetarium itself is going to be closed for maintenance. Now, during that time, we'll still be running Ancient Light, but we're also going to be doing another activity in the piazza, which is we're actually going to try to build a model of the universe, or at least a part of it. And we're going to try to represent that somehow and have people participate and make little galaxies of their own and hang them up on a web of dark matter that we're putting up on a framework. So that ought to be fun. And we're thinking about having different departments of the Academy build their own galaxies just because. Kind of like the pumpkin carving contest every Halloween. We'll see who comes up with the best galaxy. So, docents, practice your galaxy making skills. Before I go on, and maybe before we take a break, because you probably need one now, are there any questions about what I've just talked about or relating to the show itself, Dark Universe? Yes?
So one of the classic things is this discussion of there's no center, and the idea is perception of Big Bang and some point where everything came from. And I've never been able to grasp, and I've never heard a good explanation that will turn me around on it. And now this idea that it was all there and then started to cool and condense. How, I mean, that makes a lot of sense, but it still implies that there was something there to condense. And so when we talk about an age of the universe, how do you communicate that to me, much less me communicate it to the public?
We try to avoid talking about the age of the universe. We talk about when we believe the current expansion that we observe began. That's not necessarily the age of the universe. And the model of the universe changing states, suddenly becoming dense and transparent, rarefied, and cool, that really just eliminates the idea of a center of the universe. It's not commonly used, but it's an idea that was put forth, reintroduced. It had been used before, but it was reintroduced recently, earlier this year. And I think it makes sense. But certainly the idea of a teeny tiny little object over here blowing up and throwing galaxies over there is completely wrong. And I hope, one thing that they're very proud of in New York is the way they showed the different perspectives on how observers in different galaxies will see everything moving away from them. And a guy in a galaxy over here is going to see everything moving away from his perspective. I don't know if that helps you or not, but there is no center to the universe as far as we know. Yes?
One comment and then one question. It's too bad your presentation tonight wouldn't be on the DVD. We can see it again because it's so great. Thank you.
I don't know, Jim?
Is it being recorded?
Yeah, we recorded this, and then we might also be able to get the presentation uploaded as well.
Okay. And then the question I had in the news this week about that there's no real black holes, and there's gray outside the black holes, and then that's radiation probably.
That's Stephen Hawking, who said that there may be no event horizon around a black hole. How do you prove this stuff? It's all theoretical at this point. I don't know. It'll have to wait for further research and peer review, and because we can't go out and check it ourselves. So right now, it's hypothetical. Yes.
Yeah. My question was, for semantic purity, can we now change universe into a multiverse or parallel universes?
Repeat the question?
Can we change our language now and instead of talk about a universe, talk about multiverses or parallel universes? I don't think so, actually. Those are still highly theoretical. I mean, the universe is everything, including the multiverses or whatever. The one point that was very interestingly made in Dark Universe is that we can only see a certain distance, out to a certain radius. Well, somebody over here can only see to a certain radius, which might overlap our field of view. So that would mean that the universe is bigger than we can actually see. Do you call those parallel universes? I don't know. Some people may argue with me on this. I'm comfortable with one universe. Too many makes my head hurt. Way up in the corner?
We used the term, or figure, 308,000 years before light could actually be seen. That supposes that 380,000 years before life could be seen, something started.
Something started?
Well, it was 380,000
Yeah.
years old, and that started on day one.
Well, assuming that there is a beginning point to the expansion of the universe that we are now observing, the astronomers calculate that there are certain types of activity that took place from time 0 to time 1 and on, and it's calculated that up until about 380,000 years after that beginning of the expansion, the universe was simply too hot and too dense to allow light to be transmitted from point A to point B.
And does the old balloon theory still work? Of the expansion of the universe being everywhere at once?
Well, the universe is expanding everywhere at once. I've always had trouble with the balloon analogy because you're only seeing the surface of the balloon.